Bruce Nuclear Generating Station is a Canadian nuclear power station located on the eastern shore of Lake Huron, in the communities of Inverhuron and Tiverton, Ontario. It occupies 932 ha of land. The facility derives its name from Bruce County in which it is located, in the former Bruce Township. It is the largest nuclear generating station in the world by total reactor count, and number of operational reactors. Formerly known as the Bruce Nuclear Power Development, the facility was constructed in stages between 1970 and 1987 by the Provincial Crown Corporation, Ontario Hydro. In April 1999 Ontario Hydro was split into 5 component Crown corporations with Ontario Power Generation taking over all electrical generating stations. In June 2000, OPG entered into a long-term lease agreement with private sector consortium Bruce Power to take over operation of the Bruce Station. In May 2001, Bruce Power began operations. The lease is for 18 years with an option to extend a further 25 years. The Bruce Station is the largest nuclear facility in the world, comprising 8 CANDU nuclear reactors having a total output of 6,272 MW and 7,276 MW when all units are online. The Bruce Station has 3 double-circuit 500 kV transmission lines going out of it to feed the major load centres in southern Ontario, in addition to 3 double-circuit 230 kV lines serving the local area. The station is the largest employer in Bruce County, with 3,800 workers. In November 2009, the Canadian Nuclear Safety Commission renewed Bruce Power a unregistered trademark S operating licenses for 5 years, as well as giving permission to refuel Units 1 and 2. In May 2014, the CNSC extended the license to May 2015. Public hearings are tentatively scheduled for early 2015 in Ottawa and Kincardine. A new operating license has been granted for June 1, 2015 to May 31, 2020. Description: the 8 reactors are arranged into 2 plants of 4 reactors. Each reactor is within a reinforced concrete containment, with 8 steam generators. The steam generators are 12 m tall, and weigh 100 tons each. Reactors share fueling machines which travel in a duct traversing the entire plant. The duct is cut through solid rock beneath the reactors, and doubles as part of the pressure relief system, connected to the vacuum building. Each reactor has its own turbine generator set, with 1 high-pressure turbine and 3 low-pressure turbines driving 1 generator. The turbine hall at each plant houses the 4 turbine generator sets. Cooling water is taken from Lake Huron. There is 1 control room per 4 reactors. Bruce A Bruce A1, plant construction begins 1969, construction of Bruce 1 begins June 1, 1971, first criticality December 17, 1976, in service September 1, 1977, out of service December 1997. Refurbished starting in December 2010, operation resumed in September 2012, expected retirement 2043. Bruce A2, construction begins December 1, 1970, first criticality July 27, 1976, first electricity generated September 4, 1976, in service September 1, 1977, out of service October 1995, operation resumed October 2012, expected retirement 2043. Bruce A3, construction start July 1, 1972, in service 1978, out of service April 1998, returned to service March 2004, limited to 92.5% of power, planned refurbishment to begin 2019. Bruce A4, construction start September 1, 1972, in service 1979, out of service January 1998, returned to service November 2003, planned refurbishment to begin 2016. Construction of Bruce A began in 1969, making it the successor to the Pickering A plant. Bruce A units are rated at 750 MW of electricity net, and 805 MW gross. Another source gives the figures of 769 MW and 825 MW. Each reactor requires 62 40 fuel bundles that weigh 22.5 kilograms each, or about 140 tons of fuel. There are 480 fuel channels per reactor, containing 13 bundles each. There is storage capacity for about 23,000 bundles. About 16 bundles are discharged per reactor per day. The Bruce A steam generators have a separate, horizontal steam drum. This design had been dropped in most other plants at the time. Issues related to the design of the tube supports caused repair and delay costs which exceeded the net worth of the builder Babcock and Wilcox Canada. Bruce A reactors uses unique booster rods to control reactivity. Booster rods contain 93% uranium-235, and are inserted to overcome xenon poisoning. Bruce B and all other Ontario hydro reactors use absorber rods called adjusters that are normally in and are removed to overcome xenon poisoning. Bruce A demonstrated an excellent early operating history. Together with Pickeringer, the 8 units achieved an overall average capability factor of 83% over the initial 5-year period. In 1982, Unit 3 set a world record of 494 days of continuous operation. Bruce A was the most reliable multi-unit station in the world in 1984. In 1982 Bruce 2 was temporarily shut down due to a pressure tube leak. In 1986 a fuel channel failed in Bruce 2 while the reactor was shut down. Some of the fuel elements were swept into the moderator and were difficult to remove. In 1986 maintenance workers accidentally left a protective lead blanket in the steam generator of Bruce 2. By the time the mistake was discovered 6 years later, the blanket had melted, severely damaging the boiler. In 1990 a software error caused a fueling machine error on Bruce 4, damaging a fuel channel. In 1993, reactor power was reduced to 60% until various LOCA scenarios could be addressed. Subsequently Bruce A units returned to 89% of rated power. At the time Bruce Power took the lease, all Bruce A units were laid up. Bruce B Bruce B5, in service March 1, 1985, original, scheduled shutdown 2016, planned refurbishment to begin 2022. Bruce B6, in service September 14, 1984, original, scheduled shutdown 2018, planned refurbishment to begin 2024. Bruce B7, in service April 10, 1986, original, scheduled shutdown 2015, planned refurbishment to begin 2026. Bruce B8, in service May 22, 1987, original, scheduled shutdown 2019, planned refurbishment to begin 2028. The Bruce B plant stands somewhat to the south of the original Douglas Point and Bruce A plants. Construction began in 1977. Bruce B units are slightly larger capacity, 817 MW net, 840 MW gross. The slightly higher value is attributed to an improved steam generator design, where the steam drum is integral to each steam generator in a light bulb arrangement, eliminating the horizontal cross drum. With the completion of Bruce B in 1987, Bruce was the largest nuclear site in the world. In 2007 Bruce 7 was the top-performing nuclear reactor in Ontario with 97.2% performance. In 2009, Bruce 5 was first with 95.4%. In 1990, a 9-week impairment of the Bruce B containment system was created when a technician incorrectly set the calibration on radioactivity monitors. Electrical outputs by year, the station produced the following amounts of electricity: 2001 20.5 terawatt-hours, 2003 24.5 TWh, 2004 34 TWh, 2007 35.47 TWh, 2008 35.26 TWh, 2013 45 TWh, which is about 30% of Ontario's production. In 2006, OPA proposed increasing transmission line capacity from the plant, at a cost of between $200 a euro 600 million, described as the largest electricity transmission investment in Ontario in the last 20 years. The line was completed in June 2012, several months ahead of schedule. Over 700 towers were built for the 180-kilometre line to Milton. The project ranked 45th in Renew Canada's annual list. In 2010, Bruce Power was paid approximately $60 million for contracted, but unused power. Comparison with Pickering compared to the previous Pickering station, the Bruce reactors have higher power output, achieved by increasing the number of fuel channels, increasing the number of bundles per channel, and a change in the fuel bundle itself. At Bruce, the fueling equipment is shared by the 4 reactors of each plant, while at Pickering each reactor has a fueling machine. The Bruce fueling machine and fuel channel end fitting design is based on the NPD design. The Pickering design by AECL is based on Douglas Point. The design of the reactor buildings differs. Bruce uses a squarish close-in design, in which as much of the equipment as possible is arranged outside the main containment envelope for easier access during maintenance and emergencies. The steam generators penetrate the containment. The primary coolant pumps and primary piping systems are inside the containment enclosure, but the pump motors are outside containment and the drive shaft seals form the containment boundary. Pickering has round domes which enclose much of the secondary cooling equipment. The Pickering A system did not originally have a second independent shutdown system. The Bruce containment concept differs. The reactor's reactivity mechanism deck serves as a part of the containment boundary, is closer to the reactor, and more prone to damage in the event of an accident. The designers therefore foresaw the need for a second safety system to reduce the risk on an accident. Bruce received a second, fully independent safety shutdown system which uses a liquid neutron poison injection method. The Bruce system also has a high-pressure emergency coolant injection system. Each Bruce 4-pack has its own vacuum building, while Pickering has one per 8 reactors. At Pickering, the vacuum duct is closed by non-return valves, which would prevent flow of the steam-air mixture from the duct to a non-accident reactor unit following a LOCA. In the Bruce concept, there is no such non-return valve. The reactor buildings are all interconnected during normal operation. Bruce uses single-circuit heat transport system, while Pickering has 2 circuits. The first 2 reactor units of Pickering A originally used zircaloy to pressure tubes. All subsequent CANDU units use a zirconium, 2.5% niobium alloy. Bruce uses a pressurizer to maintain coolant pressure, Pickering a different system. The Pickering design utilizes 12 small steam generators operated in groups of 3. Steam generators can be individually valved out of the heat transport loop, as can the pumps. There are 16 pumps per reactor, with 4 being spare. At Bruce, the number of steam generators and coolant pumps was reduced, thereby simplifying the piping. The Bruce system permits reactor power level to be adjusted more quickly and easily. Construction costs Bruce A was projected to cost $0.9 billion, and actually cost $1.8 billion, a 100% overrun. Bruce B was projected to cost $3.9 billion, and actually cost $6 billion in dollars of the year, a 50% overrun. These figures are better than for Pickering B or Darlington. Blackout of 2003 During the Northeast blackout of 2003, 3 Bruce B units were able to continue running at 60% reactor power and at 0% grid electrical power. They were able to do so for hours, because they had steam bypass systems that were designed to decouple the reactor output from the generator electrical output. The 3 units were reconnected to the grid within 5 hours. The Bruce A and B stations were designed to operate through grid disturbances and to operate for at least 6 hours disconnected from the grid. Bruce A subsequently lost this capability due to safety concerns with the booster rod system. Contrary to popular belief, the electrical generators of nuclear plants can follow the load demands of the electrical grid, provided specific engineered systems to permit this mode of operation are included in the plant design. Refurbishment Bruce 1 and 2. Retubing of Bruce A units was planned in 1992, although this was deferred, as Ontario Hydro had a surplus of generation at the time. In late 2005, Bruce Power and the Government of Ontario committed to return Units 1 and 2 to service, in order to help meet increasing energy demand in the province of Ontario. The project was originally estimated to cost $4.25 billion. It was determined that while Units 1 and 2 could have been restarted without refurbishment, it was believed to be economically advantageous to do so, since refurbishment would have been required shortly thereafter. The goal is to keep Units 1 and 2 in service until 2043, 66 years after original commissioning. The refurbishment required pressure tube and cylindrical tube replacement, steam generator replacement, shutdown system 2 enhancement, upgrade of turbine control systems, replacing original analog controls with a DCS, significant other work and maintenance. A new fuel bundle design is being considered, which uses slightly enriched fuel pellets, within a CanFlex 43-element bundle. In 2006 and 2007, the Restart project was judged to be the largest infrastructure project in Canada by Renew Canada magazine. Estimated cost for the project later grew to $5.25 billion when Bruce Power decided to replace all 480 fuel channels in Unit 4, which will extend its working life to 2036, in line with the other 3 units of Bruce A in 2008. Due to difficulties developing the necessary robotics, the estimated cost of restarting Units 1 and 2 was raised between $400 and $700 million. The project, however, remained on schedule. The Auditor General reviewed the refurbishment deal in 2007. In January 2010, up to 217 workers were potentially exposed to radiation during the refurbishment. 27 workers may have received 5 MSV, a level well below the level that can affect human health. Only one lab in Canada was qualified to do the testing. Bruce Power had to seek permission to use alternative labs. In 2010, a plan to ship decommissioned, low-level radioactive steam generators to Sweden via the Great Lakes caused controversy. The CNSC approved the plan in February 2011. In 2011, it was reported that Unit 1 and 2 refurbishment, originally scheduled for 2009, was now predicted to be in commercial operation in 2012. In 2011, the cost had totaled $3.8 billion. The final cost was expected to be $4.8 billion. The original 2005 estimate was $2.75 billion. As of January 2011, fuel channel installation in Unit 2 was complete. The Canadian Nuclear Safety Commission gave the operator the green light to restart Unit 2 on March 16, 2012. However, the reactor was shut down the next day after a leak was discovered in the moderator system. In September 2012, Unit 1 began generating power again. On October 16, 2012, Unit 2 was connected to the provincial electricity grid for the first time in 17 years. Final costs are estimated at $4.8 billion, up from an original estimate of $2.75 billion, and the project ran far behind schedule. Future development News station as part of a plan submitted to the Ontario Energy Board for approval, the Ontario Power Authority recommended building a new nuclear power station consisting of at least 2 reactors. The leading candidate is AECL's advanced CANDU reactor. Environmental assessments are currently underway both at Bruce and at Ontario Power Generation's Darlington Nuclear Generating Station. In 2009, Bruce Power withdrew its application to the Canadian Nuclear Safety Commission for the Bruce C plant. Ontario Long-Term Energy Plan 2013 Ontario announced plans to refurbish 6 reactors at the Bruce plant. Refurbishment of Bruce A4 would begin in 2016. Other units would follow at intervals. Bruce Power estimates the refurbishment cost to be about $2 billion per unit, or $12 billion for 6. The price of the power from these units is expected to be in the range of $60 a euro $70 per MWh. Other features on site. There are more than 56 kilometers of roads on site, and at least 25 major structures. The site has its own fire department, laundry and medical center. Douglas Point encompassed by the Bruce site is the shutdown Douglas Point reactor, an earlier version of the CANDU design. Construction began in 1960. Was operational in 1967. And was shut down in 1984. The present Bruce reactors each are roughly 4 times the capacity of the 200 MW Douglas Point unit. Bruce Heavy Water Plant at one time the Bruce Heavy Water Plant also occupied the site. Atomic Energy of Canada Limited contracted the Lummus Company of Canada Limited in 1969 to design and construct the first phase of the plant, while Ontario Hydro was responsible for commissioning and operating. It was planned to consist of 4 sub-plants. A through D, A was in production in 1973, shut down in 1984, and demolished in 1993. B was in production in 1979, partially shut down in 1993, completely closed in 1997, and subsequently demolished. C was cancelled, and never built. D was 70% completed when cancelled, and subsequently demolished in 1995. During its lifetime, BHWP produced 16,000 tons of reactor-grade heavy water. Capacity of each subplant was planned to be 800 tons annum. The plant size was approximately 960 m by 750 m. The heavy water was 99.75% pure. The production of a single pound of heavy water required 340,000 pounds of feed water. Bruce bulk steam system steam from Bruce A could be diverted to the bulk steam system to provide energy for the production of heavy water, to heat buildings within the development, or to provide energy for the adjacent Bruce Energy Centre. The BEC supported industries such as greenhouses and plastic manufacturers. As one of the largest bulk steam systems in the world, this system could produce 5,350 MW of medium-pressure process steam, and had over 6 kilometers of piping. It was demolished by the end of 2006. Because of the requirement to provide steam, the Bruce A turbines are undersized relative to the reactor power. Waste storage The Bruce Station area is also the site of OPG's Western Waste Management Facility. The WWMF stores all the low and intermediate level nuclear waste from the operation of OPG's 20 nuclear reactors, including those leased to Bruce Power. As of 2009, there are 11 low-level storage buildings. In addition, the WWMF provides dry fuel storage for the Bruce reactors. The Nuclear Waste Management Organization is presently seeking a separate site in Canada for a permanent repository for the used fuel from all of Canada's nuclear reactors. OPG has proposed a deep geologic repository for the long-term management of this low and intermediate level waste, to be constructed on lands adjacent to WWMF. The proposed DGO would be about 680 meters below surface. Inverhuron Provincial Park While not part of the Bruce site proper, the nearby Inverhuron Provincial Park is owned by OPG and is on lease to the Ontario Ministry of Natural Resources. As a condition of the operating license for Bruce Nuclear, OPG has retained a 914 m radius exclusion zone in the northwest corner of the park. The former park campground was phased out in 1976 because of safety concerns related to the manufacturing of heavy water. Since heavy water is no longer produced, the park campground was allowed to reopen. The heated water released back into Lake Huron by the plant prevents the surrounding shoreline from freezing over during winter and attracts an inordinate concentration of lake fish, which in turn attracts droves of bald eagles wintering in the area. Numbers peak around late February to early March, and it is not uncommon for visitors to observe several dozen eagles in and around the general vicinity of the plant at any given time during these months. Security and safety. In 1977, 3 Greenpeace activists canoed into the site to demonstrate the lack of security. On September 23, 2001, a man whose boat capsized on Lake Huron near the Bruce complex squeezed through a gate, entered an office building and phoned for help, all undetected. The pre-9/11 mandate of the security team was to delay attackers for 17 minutes, until local police could respond. Reliance was on passive measures such as fencing and locks. The transformed post-9/11 security team is described as being larger than the police force of the city of Kingston, that is equivalent to the force of a city of 100,000. force members are permitted to carry firearms, and have powers of arrest. The force possesses armored vehicles, watercraft, and the plant is now triple-fenced. In May 2008, the Bruce Nuclear Response Team won the U.S. National SWAT Championship, defeating 29 other teams from 4 countries, the first time a Canadian team won an international SWAT event. They won again in 2009, 2010, and 2011. In 2010, about 40 contract workers were fired or suspended for inappropriate Internet usage. Post 9/11, tours of the plant area were discontinued, although there is a visitor center outside of the site. According to the Bruce County Emergency Plan, the municipality of Kincardine will coordinate the emergency response concerns of a nuclear emergency situation resulting from an accident at the Bruce Power site in the municipality of Kincardine. Kincardine is required to maintain a warning system within 3 kilometers of the plant, and has a network of 10 warning stations equipped with sirens and strobes. A variety of radiation monitoring measures are in place. Milk samples from local farms are sampled weekly. Drinking water at treatment plants in Kincardine and Southampton is sampled twice daily, and tested weekly. Groundwater is sampled from several surface water, shallow and deep well locations. Aquatic sediment and fish are analyzed, as well as livestock feed, honey, eggs, fruits and vegetables. See also, List of Canadian nuclear generating stations, List of electrical generating stations in Canada, List of largest power stations in the world, Huron Wind, Pickering Nuclear Generating Station, Darlington Nuclear Generating Station. References. External links. Bruce Power operates the plant, Ontario Power Generation owns the site, operates WWMF, Ontario Power Authority Long-Term Planning, Nuclear Waste Management Organization, Atomic Energy of Canada Limited involved with design, owns Douglas Point, Canadian Nuclear Safety Commission Federal Regulator, Kincardine Host Municipality.